Recording in progress.
Okay, it's our great pleasure to have Professor Tomotaga Kuwahara as our speaker today. Over the years, Tomotaga has been working at the interface between quantum matter, quantum information, and quantum complexity, and he has established many results that are not only useful from the fundamental conceptual perspective of quantum matter, but also from the perspective of quantum simulation and so on. For example, he had generalized the Robinson bounds for bosons and also area laws for non-energy interacting systems and so on. Today, he is telling us about his new progress. Thank you.
Okay, thank you for your introduction. It's a great pleasure for me to have this opportunity to talk to you about this work. My name is Tomotaga Kuwahara, and my operation is RIKEN, RQC, and CPR. And today's presentation title is Quantum Complexity and Generalized Area Law in Fully Connected Models. This is a joint work with Dong Hong Kim in my team, and this work was uploaded in arXiv in the last year. Okay, and today's main message is these 2 points. The first one is that entanglement area law holds without geometric structures. Usually, the area law is considered for the finite dimensional lattice systems, but in this talk, I will show that area law-like behavior holds even without geometric structure. This kind of fully connected or all-to-all interacting models satisfy the area law-like structures. And the second very important point is the local Hamiltonian problem, which is called LHP in short. And this, I will explain this LHP conjecture. And this LHP conjecture is almost true for fully connected models. And this almost means that it is not the complete solution of this conjecture. Okay, so I first show the very elementary introduction on the area law conjecture, which comes from the which is motivated by the LHP conjecture, which is originally proposed by Kitaev. And second point is why I consider generalized area law on infinite dimensional graph. Okay, so I first show what is a local Hamiltonian problem. To consider this point, I first show the K-local Hamiltonian. And K-local Hamiltonian is very general class of Hamiltonian, which includes the arbitrary K-body interactions. For example, this is the one-dimensional chain, spin chains. And in this chains, for example, this chain, this spin and this spin and this spin, for example, including interactions. Then the number of interactions, for example, this case, 3. So this kind of Hamiltonian, if I consider this kind of interaction, then this Hamiltonian is called the 3 local Hamiltonian. In typical example, we usually consider 2-body interactions. So the 2 local Hamiltonian is the most representative class in quantum condensed matter and quantum many-body physics. And the very important problem is whether we can solve the eigenproblem of the Hamiltonian. Because if we solve the eigenproblem of this Hamiltonian, we can know all the information of the spectral and time evolution and the solution of the Schrödinger equation and so on. But as you may know very well know, the n-spin system, for example, half-spin system has exponential large matrix dimension. So in the case of half-spin system, the 2 to n times 2 to n matrix. So it is usually very difficult to solve the eigenproblem of the Hamiltonian, even for very simple models. For example, the Halden conjecture is still open, even it considered very simple Heisenberg models. But this problem is open for over 40 years. Okay, and in the local Hamiltonian problem, we consider this kind of very general problem. Given local Hamiltonian H, this kind of any K local Hamiltonian, and we want to decide that the minimum energy, I mean the ground energy, is included in some energy windows from alpha and alpha plus zeta. And this zeta is the width of the energy windows. And we usually the local Hamiltonian, the ground energy have the energy from minus of the Hamiltonian norm to the plus of the Hamiltonian norm. And we want to know in where is the ground energy of this of the given Hamiltonian. So we want to know we want to decide whether the ground energy is included in these small regions. And the very important theorem by Kitaev is that the local Hamiltonian problem is usually in the worst case the local Hamiltonian problem is QMA complete as long as the energy width of the energy window is as small as 1 of the poly n, and poly n is the system size. So, and this QMA is a quantum analog of the NP class. So the QMA complete is one of the most difficult class, even for the quantum computer. So usually this local Hamiltonian problem is extremely difficult problem. However, the Kitaev theorem is regarding the worst case. So if we consider very good ground state, for example, if we consider 1D ground state, then we know that the DMRG algorithm works very well in such cases. And the very important problem here is in which case the local Hamiltonian problem is easy. And for this problem, the very bold conjecture on the local Hamiltonian problem says that if the ground state is gapped, then the complexity class of LHP is as easy as the classical case. In the 1D case, the computational class is in P. This means that we can find the ground state energy in polynomial time. And in higher dimensional case, the finding the ground energy is still very difficult, but the computational class is as easy as the classical NP class. And now the gap means that the first excited energy and the ground energy is lower bounded by some order 1 constant. And this kind of gap ground state is corresponds to the non-critical case. And usually the non-critical case is believed to show the short-range structure, for example, the clustering theorem and other kind of very good structures. But this kind of gap ground state is quite important because it determines the quantum phases of matters. So except for the critical quantum ground state, the LHP conjecture says that the complexity class of LHP is as easy as the classical case. For this conjectures, it is very, very challenging, and only a very small amount of progress has been made. And yeah, so the very important breakthrough was given around 10 years ago. And in 1D case, this conjecture was completely proven by Landau, Vajrani, and Vidic, as long as the interaction is short range. So we can explicitly construct the gapped ground state in 1D for any 1D Hamiltonian. However, in higher dimensional cases, this problem is still known to be very, very challenging. And to access this conjecture in high dimensional cases, the entanglement structure of the ground state is believed to play the key role. And in this context, one of the most important structural property of the quantum entanglement is the area law of the entanglement entropy. Entanglement area law starts from the very simple question of how much entanglement exists between the subsystem A and subsystem B when we bipartition the total system to A and B. And if the entanglement amount is very small, then it is roughly connected to the easy simulation. But if the entanglement amount is quite large between A and B, then it roughly implies that the simulation of such quantum state is quite difficult. So in this sense, how much entanglement exists is deeply related to the difficulty of the simulation of such quantum state. And entanglement area law says that if we consider the entanglement entropy between the subsystem A and subsystem B, then the total amount of the entanglement is proportional to the boundary of the bipartition between A and B. In this case, I said that the boundary of A. So, and in general case, the entanglement entropy is proportional to the total Hilbert space dimension. So, the trivial upper bound is given by the volume of the subsystem A or subsystem B. But the entanglement area law says that this, entanglement entropy is only proportional to the surface region of the boundary between A and B. And in particular, if we consider 1D systems, then the boundary region is constant size. So the entanglement area law implies that constant upper bound for the entanglement entropy. And the very important problem is in which kind of ground state satisfies the entanglement area law. And the very famous area law conjecture implies that if the ground state is gap or the non-critical ground state, then the entanglement area laws holds for arbitrary quantum many-body systems. In other words, the entanglement entropy is order of the surface region of the subsystem A or subsystem B. And as I explained, the gap means that the first excited energy and the ground energy is lower bounded by some order 1. And the entanglement structure is so far proven only for 1D systems in general case, for example. But in 1D cases, originally the proof is given for short-range interaction systems, but this kind of proof is generalized, for example, long-range interaction system, bosonic interaction system, or the infinite system size, and only from the clustering of operations. So the understanding of the entanglement area law in 1D system progress so much. But in contrast, in 2D systems, the entanglement area law conjecture is quite challenging, even for the proof of the subvolume law, which is the intermediate scaling from between the entanglement area law and the volume law. And the establishment of the subvolume law is still very, very challenging. And so far, only the conditional proof was given. For example, the low density of the low energy state, or the under assumption of the adiabatic path from the trivial state to the target quantum state. And the most important progress is given by Ansh, Arad, and Gosset in 2022, and they proves the entanglement area law in 2D systems only from the assumption of the fluctuation freeness and the local gap conditions. And in this case, I said that the gap is defined by the ground energy, the difference between the ground energy and the first excited energy. But here, I assume that the ground state is non-degenerate. But usually, the entanglement area law is conjecture is believed to be true even for degenerate ground state. And in 1D case, this kind of degenerate ground state was indeed treated by Arad in 2017 and 2023. Okay, so in this slide, I want to explain why the entanglement area law is important. And for this question, the rough answer is that the entanglement area law is the the necessary condition for the tensor network representations. This means that if the ground state is efficiently described by the tensor network means PEPs, projected entanglement pair state, or the matrix product state, and so on. This is a generalization of the NPS and PEPs. And this kind of tensor network is the primary numerical technique to numerically simulate the quantum ground state. And if the ground state is efficiently described by tensor network, then we can easily prove that the ground state satisfies the area law. In this sense, we say that the entanglement area law is necessary condition for the description by the tensor network. So by taking the control position, if the entanglement area law breaks down, in such case, the ground state is not efficiently described by the tensor network. So if we could find some ground state class which breaks down the entanglement area law, then for such ground state class, all the algorithm and the classification based on the tensor network also breaks down. So in this sense, we hope that the entanglement area law holds for arbitrary quantum ground state and the gapped ground state. For this reason, the entanglement area law is regarded as cornerstone in quantum many-body, modern quantum many-body physics and condensed matter physics. And most of the researchers believe that entanglement area law is true. And another important notice is that the entanglement area law is necessary condition for the efficient description by the tensor network. But the converse is not true in general. Even the ground state satisfies the entanglement area law for arbitrary linear entanglement entropy, but we can find some quantum ground state which cannot be efficiently described by the tensor network, which was given in 2016.
Sorry, question. I thought there's a proof saying if for any index smaller than 1, the area law holds, then at least in 1D there's MPS. That's okay.
Oh, sorry. You mean? Sorry. Could you?
You said even for any Rayleigh index, if the Rayleigh entropy satisfies the area law, that's not enough to guarantee.
Sorry. This means in the 1D case, if the linear entanglement for alpha is smaller than 1 satisfies the area law, then MPS description is possible. But this means the 2D case.
Oh, I see.
So,
thanks.
yeah. And now I consider the entanglement area law in finite dimensional lattice system. But this kind of entanglement area law is, extended to more general setup. For example, we consider the 4-body system, A0 and B0 and small a and small b. And small a and small b interact with each other. And in this case, we ask, in this case, the small a and small b play the role of the surface region, and A0 and B0 is like bulk regions. Then the very natural question is that if the ground state is gapped, then the entanglement entropy of this ground state is also proportional to the logarithm of the dimension of small a or small b. And if this kind of generalized area law is true, then the arbitrary dimensional, finite dimensional entanglement area law is also true. Yeah, this is very trivial, but it is very challenging problem whether this problem is true or not. And this kind of generalized area law was first proven for thermal area law in the thermal state, quantum thermal equilibrium state. In this case, instead of the entanglement entropies, the mutual information is considered. So if we consider the quantum given state in this 4-body setup, and then considering the mutual information between A and B, then the entanglement, this kind of generalized area law is rigorously proven. And also, other case such that the generalized area law is true is the dynamical system. If we consider the quantum dynamics in this 4-body systems, and then considering the entanglement generation by the dynamics, then in this case, the entanglement, the generalized entanglement area law is also proven for dynamical, the generation of the dynamical generation of the entanglement entropies. So in this sense, the thermal equilibrium and the quantum dynamics satisfy this kind of generalized area law, but it has been open problem whether the generalized area law is true for gapped ground state. And for this question, the ground state is for the gapped ground state, the generalized area law was disproven in 2014. So in their paper, they construct explicit counterexample such that the gapped ground state breaks this kind of generalized area law. In other words, the entanglement entropy between A and B is proportional to the total Hilbert space dimension of the subsystem A or subsystem B. So in this sense, the generalized area law is true for dynamics and thermal equilibrium, but not true for the gapped ground state. And my question is that if we consider the very general four-body cases, the generalized area law is not true. But we still have the possibility that the generalized area law may be rigorously proven in some specific class of the ground state. And for this candidate, we consider the free connected graph. The free connected graph means that any of the sites is connected to each other. So this kind of system is also correspond to the all-to-all interaction systems, and this includes, for example, Sherrington-Kilpatrick model for spin graph, Lipkin-Meshkov-Greek model for cavity systems, and Sachdev-Kirchhoff model for the black hole models. And this kind of all-to-all interaction system interaction model was established so far. And this all-to-all interaction is regarded as a useful platform, for example, the quantum computing and quantum chemistry. And in the classical theories, this kind of all-to-all interaction system is known to have very simple structures. For example, even in the quantum cases, if we consider all-to-all interaction systems and then consider the product state approximation of the ground energies, then it has been known that for arbitrary quantum Hamiltonians, the error is at most n to the power of 2/3 instead of the order n. And if we assume the gap conditions, the product state approximates the ground energy up to the error of the square root of n. Square root of n and n to the power of 2/3 is still very, very large, but much smaller than the total system size. So if we want to approximate the ground state, energy density of the ground state, then we can approximate it for arbitrary small errors, constant errors. And for this kind of free connected model, several classical simulation was also established. For example, in the Brady's paper, they considered that the computation of the partition function is within polynomial class, p-tat class. And this paper also shows a numerical demonstration such that the DMRG algorithm will approximate the ground energy. So my question is whether in this kind of free connected models, the generalized area law may hold. But at first glance, we cannot see any boundary between A and B because all the qubit interact with the A and B. All the qubit in A connected to all the qubit in the subsystem B. So in this sense, there are no boundaries, and the entanglement area law implies the volume law between the A and B. However, if we effectively map the Hamiltonian to the constant size boundaries, for example, like this form, then the total Hamiltonian is decomposed to HA plus HB plus small HAB. And now, if the small HAB has, for example, small Schmidt rank, order 1 Schmidt rank, then this kind of Hamiltonian corresponds to the small boundary sizes. then in this case, we may still expect that the generalized area law may give the constant upper bound of the entanglement entropies. And purpose of this talk is, of this work is to prove the generalized area law in free connective models for arbitrary Hamiltonians. And the second question is, second purpose is to establish the efficient classical description of the gap ground state. In this case, I aim to establish the MPS description of the gap ground state with the precision guarantee. Okay, so I will show the setup and main result. The setup is a free connected model with small Schmidt ranks. And the main result is a generalized area law and matrix product state approximation of the gap ground state. And the setup is the arbitrary many-body Hamiltonians, and the total system size is small n, and lambda is the total system, set of the total site or the qubit. And here, for the simplicity, I denote the two-body interaction. HII dash is the interaction between the site I and site I dash, and HI is the local potential. And all the result is generalized to arbitrary k-body interaction. And also, as an important notation, I introduce a subset interactions. This one is denoted by HAB. And this pick up all the interactions between the between the site I in the subsystem A and site I dash in the subsystem B. And the ground state is denoted by capital omega, and the spectral gap is denoted by capital delta. And now entanglement entropy is given by the standard form. And as a very important assumption, I consider small Schmidt rank. I mean, for arbitrary subset interactions, subset interaction is given by this form, and we can formally decompose this interaction to this form. HAS is one local Hamiltonian, and HBS is also one local Hamiltonian. And yeah, and in this case, and we assume that the summation of the JS, the coefficient JS, is upper bounded by some constant. So if the Schmidt rank between the system A and system B is some constant, then this condition is always satisfied. But at least we assume that this constant coefficient JS linearly decays. Then this assumption is satisfied. And this condition is usually satisfied for arbitrary uniform all-to-all interacting models. For example, if we consider Lipkin-Meshkov-Glick models, this LMG model is all-to-all interacting XY model. So the Hamiltonian is given by this form. And by decomposing this Hamiltonian to this form, then we can easily say that the DH Schmidt rank between A and B is equal to 2, and G1 bar is given by Jx plus Jy. So the LMG model is one candidate such that the assumption is satisfied. And it is very important to note that the SYK model does not satisfy these conditions. If we consider this kind of decompositions, we have to take the absolute summation of the absolute value of Js, but the SYK model includes the random interactions. So this kind of random summation, the SYK model is normalized in terms of the summation and the random and the summation of the random variables. So the normalization factor is given by n to the power 3 over 2 instead of the n to the power 3. So unfortunately, the SYK model is not included in our setup. But for example, if we consider the disorder-free SYK model, then we can prove that this kind of disorder-free SYK model satisfies our condition. And whether the SYK model also satisfies generalized area law or not is quite important open question. And here I consider the upper bound of the JS is satisfied and upper bounded by some G1 bar. But we expect that this condition can be removed, or in rigorously speaking, not removed but relaxed. We only proves we may only require the condition such that the HI, the norm of the local interaction is smaller than or equal to J over N will be enough. And if we could improve the assumption, then the result is applied to much more broader class of the auto-interactive model. And the main result of this work is the generalized area law up to polylog factors. For arbitrary gapped ground state in the previous setup, the entanglement area law is upper bounded by this inequality. And this alpha 1, alpha 2 is some order 1 constant, and FG1 bar and delta is depend on the assumption and the property of the assumption and the spectral gap delta. But anyway, if the delta and G1 bar is constant, then this one is a polylog n upper bound. This gives the polylog n upper bound for arbitrary constant spectral gap. So we prove the entanglement, generalized entanglement area law up to some polylog factors. And very natural question is whether this kind of entanglement area law, the generalized entanglement area law is optimal or not. But as far as we perform the numerical calculations, the entanglement area law may obey the constant upper bound instead of the polylog n type upper bound. So in this sense, we assume that we expect that the generalized entanglement area law may be further improved to the constant upper bound. And very important open question is what is the optimal upper bound for the entanglement area law in fully connected model?
Sorry, excuse me. Could you please go back to the previous slide? Yeah. So what is no, the next one.
Okay.
What is the G1 bar here, and what is the delta?
Sorry, G1 bar is defined in this assumption.
Oh, I see.
Yeah. So this is roughly speaking, this is the interaction strength, and delta is the spectral gap. Yeah.
Oh, I see. And why do we have these weird figures in the coefficients? I mean, why do we have these weird numbers in these coefficients? I mean, they look weird, and I cannot understand.
Oh, this one? Oh, yeah. This one is very, usually we said that this is a kind of constant, but by rigorously estimating the constant alpha 1, alpha 2, then the upper bound become very, very weird values. But I think the constant value is no longer optimal because this one is extremely large.
Sorry, and what is E and K here?
E and K. Oh, sorry. E is the natural.
I see.
Yeah. And K is the the Hamiltonian locality.
Oh, okay.
Hamiltonian includes K-body interaction.
I see. Thanks.
Yeah. And the second result is the matrix product approximation of the free connected models. To describe the ground state by MPS, we first label each of the sites on the 1D chain. So 1, 2, 3, 4, 2. In this picture, up to 20. And now for this kind of 1D arrangements, we can prove that the gapped ground state is well approximated by some MPS, which is noted by omega d. Omega d is the bond dimension of the MPS, and the approximation error is now given by delta times the region size x, and this inequality is achieved by choosing the bond dimension like this form. And if the delta is some order 1 constant, then we can say that the bond dimension is still quasi-polynomial. So exponential polylog n type bond dimension is enough to approximate the gapped ground state. In this sense, MPS is, and the important point is that MPS is classically simulatable by computational time like n times d to the power of 3. So in this sense, the gapped ground state is simulatable by using the computational cost like exponential polylog n. And this also partially gives the theoretical justification of the numerical successes using the DMRG algorithm. Of course, we don't show, we only prove the existence of the MPS, but it is completely different problem whether we can efficiently find the MPS approximation for the gapped ground state. And this point is deeply connected to the LHP conjecture. The LHP conjecture says that if the ground state is gapped, then the complexity class of LHP is as easy as the classical cases. And in high dimensional case, the ground state calculation is within the NP class. And now, this kind of MPS approximation implies that the ground state is classically simulatable up to by using some quasi-polynomial time scale. So in this sense, we can say that LHP conjecture of the dense graph is almost true. If we completely say that this is true, then we have to prove that the MPS description is efficiently performed by the polynomial side with respect to the system side. So if we want to completely prove the LHP conjecture on the dense graph, we have to improve the current result from the quasi-polynomial form to the polynomial form with respect to the system size. This is also very important open question. Okay, so I show the main technique to derive the generalized area law in the free connected models. And for this purpose, I utilize the mean field renormalization group technique. I will explain this point. I first consider mean field approximations. This means that we approximate the ground state by using the product state. And the choice of the product state is given by the Schmidt basis with the largest Schmidt coefficient. That means that, for example, if we consider the Schmidt decomposition between the site I and the other regions, then we can consider the Schmidt decomposition like this form. And now lambda s is ordered like lambda 0 is the largest. And I employ the Schmidt basis with s is equal to 0 as the mean field basis. And by using this, taking the Schmidt decomposition for all the sites, then we can get the ingredient for the mean field state. And usually, we can prove that the computation of the mean field state is NP hard, even for classical cases. So in this...
Just to clarify, here do you mean the state of the entire system, this mean field state for the entire system is the tensor product of the 0 for each side?
Yes, so the true ground state is not satisfied, not given by the product state, but we want to approximate the total ground state by the product state of the zero state.
Thanks.
But of course, the product state approximation is not so good to completely approximate the ground state. So by using this mean field basis, we further renormalize the Hamiltonian. And for this purpose, I first decompose the total system into many blocks, and block is now described by the capital LS, and each of the block size is given by n to the power 1/8. So the number of block is now proportional to n to the power 7/8. This 1/8 choice is for the analytical convenience in the afterward calculations. Yeah. And now the block size is given by n to the power 1/8. So the block Hilbert space dimension is still quite large. This means that exponential order of the n to the power 1/8. This is sub-exponential. So we only pick up the quantum state such that only a few sites deviate from the mean field state. So almost all the quantum state is given by the mean field state, but we allow only at most z state, in this case 2 state, is deviate from the mean field state. Then we only pick up the quantum states such that this state, z site is deviate from the mean field state. Then the total number of such state is given by d to the power of z. D to the power of z means this is the total number of the Hilbert space dimension of this z site, and n to the power of z8 is the combination such that picking up z elements from the one blocks. So if we only consider the small number of Hilbert space bases, then the total Hilbert space dimension in the renormalized basis is still upper bounded by polynomial size with respect to the system size. And by using this renormalized basis, we consider projection for each of the blocks. This projection pi ls smaller than z means that we only pick up the quantum state which is at most this state is deviated from the mean field basis. And we taking all the projections, and then by using this renormalization projection, we construct the renormalized Hamiltonians. And now, in this case, one block constitutes a new qubit. So the new qubit interaction is given, characterized by the block-block interaction between the block LS and block LS dash. And now the block-block interaction is now characterized by like this form. So this is a renormalized qubit interaction. Now the qubit Hilbert space dimension is at most poly n. And by repeating the same process, we first consider the original Hamiltonian, and then by using the renormalization, we consider large block, but the large block has the polynomial basis. And then for this renormalized Hamiltonian, we also construct the mean field basis, and then we construct the block and truncating the Hilbert space dimension, and then construct the new renormalized Hamiltonian, and so on. And then in each of the steps, the system size becomes the power of 7/8. So in the first step, the system size becomes n to the power of 7/8. In the second step, the Hilbert space dimension becomes n to the power of 49/64. And after the S0 renormalization processes, we can prove that the total system size is given by n to the power of 7/8 to power S0. Also, the renormalized qubit dimension is given by like this form. In the first step, we can prove that proves that d to the power of z times n to the power of z/8. And this Hilbert space dimension becomes the local qubit dimension. So in the second step, we prove that the total Hilbert space, the local qubit dimension becomes like this form. And by repeating this process, the total qubit Hilbert space dimension is given by dn to the power of c to the power of s0. And now z is some order 1 constant. So by choosing S0 is proportional to log n, then the total system size is order 1. And the renormalized qubit dimension is also given by z to the power of S0 is polylog n. So the final dimension is given by dn to the power of polylog n. So
question? Just want to clarify, is this projection some analog of the technique of approximate ground state projection method, which you used before in this fully connected model?
This process itself can be applied to arbitrary quantum many-body systems, but the very important point is whether we can establish the efficiency guarantee of this process.
And what?
Efficiency guarantee, because we only truncate the Hilbert space dimensions, but we cannot know whether the final renormalized Hamiltonian gives a similar ground state to the original one. But the very challenging problem is rigorously prove that the ground state of the final renormalized Hamiltonian is still very close to the original ground state. And this is only possible for the orthogonal interacting system.
Oh, I see.
Okay, so the main technical challenge is error guarantee for the truncation of
I have one more question. Here I think you want to use this to when you say ground state is very close to the original ground, the new state is very close to the ground state. I think you mean the difference in the trace norm of the reduced density matrices. The difference of the reduced density matrices has a very small trace norm.
Yes.
And to translate this into a entanglement entropy bound, do you need to use something like the fairness inequality?
Yes. So in this sense, we truncate the Hilbert space dimension in the renormalization process, and we have to ensure that this kind of truncation of the ground state still maintain the ground state property to the very close to the original ground state. Then in the final Hilbert space dimension is given by exponential log polylog n. And as you say, we have to utilize that the original ground state and the approximate ground state is very close. So we can prove the upper bound of the entanglement entropy. But
they are very close in terms of the trace norm difference.
Yes.
So then you use the fairness inequality to further.
In fact, we don't utilize the fairness inequality, but we utilize very, very close techniques. Yeah.
I see.
Okay. And technical, I don't have not so much time, but I already show very roughly shows how to get the efficiency guarantee for the mean field renormalization groups. The first very important ingredient is the variance gap trade-off inequalities. For arbitrary local operators, this AL is k-local operator on subsystem L, and delta is the spectral gap of the total Hamiltonian. Then delta times the variance of the local operator. Variance is taken for the ground state. And this is upper bounded by constant time G1 bar times the total system size. Total subsystem size L. Usually the variance AL has the trivial upper bound of the L to the square. So this means that as long as the gap is delta is order 1 constant, then the variance of the AL is always any k-local operator have only the fluctuation square root of the system size, subsystem size. And by using this trade-off inequality, we can prove the approximation error using the mean field approximations. And by defining this approach, we can also prove this kind of robustness inequality. Robustness means that for arbitrary local unitary operators on the ground state, the ground energy is not changed so much. And this unitary operator preserves the Schmidt basis. Then the ground energy is almost equal to the original ground energy. And this robustness is characterized by the square root of n. So from this robustness inequality, we can prove that the ground state is locally disentanglement, almost locally disentanglement, in the sense that by using this robustness inequality, we can prove that the largest Schmidt coefficient, lambda 0, is larger than 1 minus delta log over 2 delta. And now delta log is now 1 over square root of n. So we can prove that the largest Schmidt rank is almost equal to 1, up to the error of 1 over square root of n. So from this point, we can prove if So from this kind of the inequality, we can prove that the local quantum state is almost given by the product state. So as long as we look at the small block, the block size is much smaller than square root of n, then we can also prove that the local blocks, on the local block, the ground state is approximated by the product state up to the error such that the subsystem size times the delta log. And this one is almost equal to 0, as long as the subsystem size is much smaller than square root of n. However, in order to perform the Hilbert space truncations, we have to derive the probability distribution to observe deviation from the mean field state. So not only the expectation value, we have to access the probability distribution of the deviation. And this problem is equivalent to obtaining the probability distribution of the one local operators of this ML, and L is some block, and 0 is the mean field basis on some site I. So if the quantum states satisfies if the site I state is rigorously given by the mean field state 0i, then this term is equal to 0. So in other words, this ML is minimized by the product state of the mean field state, mean field basis. And we can see that the ground state approximately minimizes this ML because the ground state is given by, approximated by the product of the mean field state on the subsystem L, as long as the subsystem L size is smaller than square root of n. And we can prove that arbitrary one local operator ML satisfies exponential concentration with a variance square root of L over delta. But this variance is still very large because L is now as large as the power of the total system size. So we have to define this kind of exponential concentration, and we can define this exponential concentration to the strong decay like this form. And this characterizes the probability to observe the eigenvalue of ML, which is larger than some constant z. And if the eigenvalue of ML is larger than Z, then this means that more than these sites have to deviate from the mean field state. So the probability to observe the eigenvalues of ML is larger than Z is probability to observe the more than this site is deviated from the ground state, the mean field state. And also, now the delta log is proportional to 1 over root n. 1 over square root of n. So this decay rate is roughly given by this form. So if we choose the block size L is as large as n to the power 1 over a, then we can prove the decay rate is given by n to the power minus 1 over a to the power of z. So in order to ensure the error guarantee like 1 over poly n, then it is enough to choose these order 1 constant. So from this upper bound, we can rigorously ensure that the Hilbert space Hilbert space truncation in the block, which is achieved by these constants. Constantly, yes. And second problem is the renormalized interaction amplitude. In the mean field renormalization group approach, we consider the block as the new qubit. So the new qubit interaction is now described by the block-block interaction. For example, in this case, L and L dash. But now the block-block interaction strength is usually upper bounded by like this form. So the block size L times block size L dash over N. So the new qubit interaction is highly amplified. So it is very difficult to get the error guarantee for the renormalized Hamiltonian for the Hilbert space truncation. So the very important problem is to suppress the interaction amplifications. And for this point, we consider the appropriate decomposition of the block-block interactions like this form. H tilde L is arbitrary block, the internal interaction in the block, and H tilde L dash is also the internal interaction in the block. And delta HL dash characterize the block-block interaction between L and L dash. And the very important point is that we can prove that the delta HL dash is amplified only by Z times. Z is the number of flips in the each of the block, and Z is some order 1 constant. And by rewriting this form, then N over L is the total number of the renormalized qubits. So we can prove that the renormalized qubit interaction is now proportional to Z over the number of renormalized qubits. So we can prove that the interaction amplification is at most Z times, and Z is some order 1 constant. So the interaction amplification is inevitable in this case, but the amplification, amplification is not so serious because the renormalization process repeat at most order of log n times. So by using this kind of renormalization processes, we can prove that in each of the renormalized Hamiltonian satisfies a good truncation error of the Hilbert space dimension. Okay, so I will summarize the talk. The first, in this talk, I first show the motivation of the local Hamiltonian problem. And the LHP conjecture says that the gapped ground state is as easy as the classical case. And if we consider the fully connected graph, we can prove the generalized area law and good MPS approximation. The generalized area law means the polylog n type upper bound, And the MPS approximation is possible by quasi-polynomial on dimension with respect to system size. So from this point, we can prove that the LHP conjecture of the free connective graph is almost true. So, and we can say, yeah, non-critical ground state have quasi-polynomial complexity. And the important open question is whether we can improve the the polylog n type upper bound to the optimal form, which may be given by constant upper bound. And the second point is also relevant, but the very important problem is whether we can improve the upper bound to the polynomial form, which also implying the complete solution of the local Hamiltonian problem conjecture of the free connected model. Okay, so thank you for listening.
Okay, thank you, Tomataka, for the very interesting talk. Any further questions? I have some questions. The first question is, you mentioned in 2 dimensions, even if for any Renyi index, the Renyi entropy satisfies the area law, is not enough to have a tensor network. Here, when you say tensor network, do you mean PEPs or do you mean any tensor network?
Oh, I think in this case, we have to consider two-dimensional tensor network. So in this sense, in the paper, they consider the PEPs, 2D PEPs. So as you say, it may be possible if we consider the high-dimensional tensor network structures, then the 2D system may be efficiently, described. But I'm not sure. Yeah, it is. I'm not sure, but it is very unlikely. Yeah.
So suppose we focus on PEPs. Now that we know the entanglement area law is not enough to guarantee the efficient representation, then what do you think is the sufficient condition?
Oh, yes. So maybe only the entanglement area law is not enough. But if we consider the gap ground state, then I believe that the tensor network representation is always possible by using the gapness instead of the only by utilizing the entanglement area law, but we also utilizing the gapness condition and the condition of the local Hamiltonian structures. Yeah, but yeah.
I see.
But so far, this is very difficult open question.
Yeah, any other questions? I have another question. So previously, people were proving area law for 1D system, and now in this talk, you discussed the area law for fully connected systems. But suppose I just want to consider 2D, 3D local systems. And so far, the area law has not been proved. What do you think is really the main difficulty?
Oh.
I think within the approach of approximate ground state projection, the main difficulty is to estimate, to upper bound the Schmidt rank of the projector.
Yeah, usually now the most promising way to prove that high-dimensional entanglement conjecture is utilizing the AGSP formalism. And the primary obstacle is to get a good AGSP. So error is sufficiently small, but the Schmidt rank is not so large. And so far, whether we can, construct we can find the non-trivial construction to get a good AGSP is the primary obstruction. Yeah, but I'm not sure whether the AGSP approach is the only way to prove the high-dimensional entanglement high-dimensional entanglement area law conjecture.
Yeah. Yeah, any other questions? Okay, if not, we'll thank Tomataka again. Thank you for the very interesting talk.
So thank you very much.
Yeah. So we will log off. See you.
Okay, so see you very much.
Record.